Right. So one thing I enjoy about chemistry is we learn a lot of concepts, but then we also get down to the numbers. We also do a quantitative reasoning between things. And so I like chemistry because it combines those two elements, whereas some other sciences maybe are focused more on one than the other. So anyways, last time we talked about the phase changes and just, a concept type of view and in a qualitative type of view. But now we're going to take a more quantitative point of view. So again, I've copied down this heat chart right here. And then we can think about how much heat is added, what's the energy added to change the temperature of our compounds. So if we think about this chart, in different areas of the chart, different equations will apply. So when we have the temperature changing with heat added, we've actually already covered that mathematical part of the chart, and that's our Q equals MC delta T, right? The amount of heat added is going to change the temperature of the solid, and that depends on what kind of compound you have and how much of it you have, right? So you have all that part of the equation. And then we can think about the other parts of the equation, right? So here we have from a solid to a liquid. And then up here we have a liquid to a gas. The way these parts of the chart are treated a little bit different. So we have this orange part from a solid to a liquid. Instead of calling that melting, it's usually called fusion when we're doing these mathematical calculations. Don't ask me why, it just is. And then same thing from liquid to gas. Instead of being called boiling, we generally call that vaporization when we're doing the kind of math here. And we have a value here that's dependent on what kind of compound you have. So of course, we're going to take a look at water because that's the most common thing on Earth. And so in order, some data for the fusion, the vaporization, how much energy does it take to either melt or boil something? For the melting, we have the delta H of fusion. And then for the boiling, we have the delta H of vaporization. And these delta H's, what they mean is it's the energy required for, in this case, 1 mole of material to change phases, right? And so you can see that's kind of similar to our Q equals MCAT. Here, obviously, we're not changing temperature, so we wouldn't have a delta T, but instead what we have is a change in phase. Here we have this C that was specific for every material. Here we're going to have a delta H of fusion and vaporization that's different for every material. Here we were talking about in terms of mass, but here instead we're going to be talking about in terms of moles. But of course, we can easily convert one to the other. So anyways, let's take a look at what these values are for water. So water's heat of fusion or enthalpy of fusion, whichever way you want to say it, is 6.20 kilojoules per mole. So it takes 6.02 kilojoules to melt 1 mole of ice. And then for vaporization, it's 44.0 kilojoules per mole. So one thing that you'll notice with almost every compound, the delta H of vaporization is much greater than the delta H of fusion, right? The fusion is 6, the vaporization is 44. That's quite a big difference. And so let's think about this logically. Does that make sense? And if you think about it, yeah, it actually does. For a gas, in order to go from a liquid to a gas, we have to completely break the IMFs. Right? Because in a gas, there basically are no intermolecular forces. The molecules are too far apart to interact with one another. Whereas when we're going from a solid to a liquid, all we have to do is weaken these intermolecular forces, right? Both solids and liquids still have plenty of intermolecular forces. They're still interacting with one another. The only difference is that in the liquids, the intermolecular forces have been weakened. So now the molecules are allowed to roll around one another. So let's take a look at an example question that you might be asked. So it'd be something like, how much energy in kilojoules, of course, is required to turn 20.0 grams of water into steam, right? So again, A big thing in general chemistry is going from these word problems to then some sort of mathematical equation or some kind of, math, and then end up with some kind of numerical value. So if we think about what we have here, what our question is asking is water into steam. What kind of phase transition is that? Well, that's boiling or vaporization. So what value do we want to use? We want to use our delta H of vaporization. So we can write that piece of data down. So delta H of vaporization for water in this case is 44.0 kilojoules per mole. And then we look at what other thing we're given in the question to turn 20 grams, right? So we have an amount, but then note that this is in grams while our delta H is in moles, right? They're not the same unit. They need to be the same unit in order for them to, talk to one another and be able to do math. Of course, we can convert grams to moles. We know how to do that. So we have 20.2 grams of our water. And anytime to go from grams to moles, we use the molar mass. In this case, the molar mass of water is 18.02 grams per mole. And right, you can see at this point, we should be able to go from grams to moles and vice versa very easily. If this is something that you're still struggling with, you really gotta, catch up, stop by my office hours or see a tutor, because this is, a fundamental part of the course at this point. And so then grams and grams cancel out, and now we're at moles. And then if we think about this, right, this is a unit over another unit, we can then use that as a conversion unit. So since we have moles up top here, we're going to want to put moles on the bottom here and then kilojoules on top. The numerical value, the 44, always goes with the top unit. So that goes with the kilojoules. So we put 44.0 kilojoules up here. And then moles and moles go ahead and cancel out. We plug that into our calculator and you get 44.8 kilojoules as your final answer.